Okay. So today we're going to complete the proof of the second welfare theorem. So the first part is just the big part of the proof, which is about you have a primitive of preferences, production sets, endowments, and then we assume that the production set is convex, and every preference relation is also convex. So remember, this has its upper contour set of preference is convex and is locally non-satiated. Then for every Pareto optimal allocation, there is a price vector, not necessarily positive, right? Such that X star, Y star, and P is a price quasi-equilibrium transfers, okay? Now, in order to do the proof, we're gonna use this separating hyperplane theorem that essentially says that I can separate a point from a convex set through a hyperplane, right? So you need essentially convexity. So the whole game here is going to be to convert this price quasi-equilibrium any allocation, right? That is Pareto, we're gonna make it essentially a convex set. And then we are going to use that idea to be able to separate a point from that. So that's the geometric intuition. So define for every individual the set VI. So VI is going to be the set of all alternatives that are strictly better than X star. So X star is essentially the allocation that I am trying to implement through price quasi-equilibrium with transfers. And then I'm just looking at all set of allocations that are strictly better than the X star, okay? Then I'm gonna define the following set, which is capital V. The set capital V is the summation of all sets capital V sub I. Now, this set is constructed in the following way. So any element here is going to be the summation of x's where each x sub I belongs to each of these V sets. Okay, so in other words, if I take an element on V, this element can be constructed as the summation, okay, of elements in the sets VI. Okay. So in other words, why can I add things here? Remember that these are commodity bundles, so commodity bundles live in the reals, right? So addition is well defined, then I'm just adding commodity bundles. Now, capital Y, the same idea. I take all production sets and then any element in capital Y, it has to be supported as the summation of elements in each Y sub J, okay? So the interpretation of the second one is easier because this just tells you that this is the kind of aggregate production set. So this can be supported as the production of each individual firm, right? So it's a feasible plan in the economy, in the aggregate. The first set, the V set, is harder to understand intuitively, but mathematically it's very clear, right? So it's just the summation of the sets VI, and each set VI is the upper contour set, okay? Now the set Y plus omega is the shifted production function by the endowments, right? So so you just take the aggregate production set Y and then you shift it by the endowments of the goods. So that gives you the total amount of physical goods in the economy. Now, so what I want to do, remember the objective here is that if I have an economy with preferences, production plans, and then with assumptions of convexity, then for every Pareto optimal allocation, there is a price vector P, right? That you can implement that particular allocation. So the step one is essentially, I want to construct, so all these steps are going to be done in order to recover a price, right? System, right? So we're gonna recover a price system that will support any Pareto allocation, right? So we want to show, that's the WTS, we want to show that every set V sub I is convex, right? So this follows from the preference being rational and convex. Suppose, for instance, that Xi is strictly preferred to Xi star, and X prime I is strictly preferred to Xi star. Then take a mixing parameter alpha, and we want to show that the combination of X and X prime is strictly preferred to X star. So given the completeness of preferences without loss of generality, we can assume that Xi is weakly better than Xi prime. So without loss, it's just an additional assumption I make that is not reducing the generality of the statement. By convexity, we have that this mixing of x and x prime is weakly above, right? Convexity, remember, is all about the upper contour set with weak preferences, right? So that's the only thing that this gives you. But transitivity yields the desired conclusion, right? Because essentially you have now that the mixture of these two things is going to be strictly better than, let's say, I star. Okay, so with this in hand, right, we essentially have that the upper contour set, strict upper contour set V, is in fact a convex set. Now the sets V and Y plus omega are convex. The sum of convex sets is also a convex set. So this is easy to see, right? So if you have convex sets and you add them in this form, then the result is a convex set. So what we want to do is the following. So you have two sets. You have the set V and the set Y plus omega. Now, this separating hyperplane theorem essentially has two forms, right? One is separating a point from a convex set. Another is you can separate two convex sets. You can separate two convex sets as long as they have an empty intersection, okay? So what we want to show in step 3 is essentially that the intersection of V and Y plus omega is empty, okay? So why this is empty? Well, this is a nice thing about Pareto optimality. So remember, what is the definition of Pareto optimality? Pareto optimality says, right, that there is no other allocation that is strictly preferred for at least one individual, right, and weakly preferred for the rest, and that it is feasible, right? So remember that feasibility is captured in Y plus omega, right? So the set Y plus omega essentially captures feasibility, right? The set B captures the allocations that are strictly better off, right? For at least one individual. So Pareto optimality is essentially saying that the intersection of capital V with Y plus omega is empty. So you cannot improve an individual I is strictly better off, right? Without getting out of feasible allocations. Do you understand? So step 3 is crucial, right? But it's just a very geometric way of seeing Pareto allocations, okay? This is Pareto optimal. Essentially, it says that this set capital V and the set Y plus omega, the intersection is empty, okay? Great. So the separating hyperplane theorem is almost there. So we have essentially two convex sets. The intersection of the convex sets is empty, right? So now you can apply the theorem. So this is just a result from convex analysis. The result essentially says that if these two things happen, so two convex sets that have an empty intersection, then there is a vector, right, a hyperplane. And essentially hyperplane is captured but essentially the number R, right, and the price vector. And then you essentially said that it has to be that any element in capital V, it has to be that multiplied by times the vector, right, is greater than equal than this constant R. And the same thing happens with the other set with the opposite sign. So P times Z is less than equal than R. And essentially this second element belongs to the capital Y plus omega. So geometrically what we're seeing is that you have two convex sets and there is a line passing through them. So at this stage, right, I'm gonna make a small stop. Then I'm gonna go to the iPad. So I ask you to read the separating hyperplane theorem from Mascolel's mathematical appendix. So did someone did that? So who can tell me a little bit about the separating hyperplane theorem before I go to the drawing part?
Victor, I got a question. So in the case that, you know, that we have that P times S was in one case greater or equal, in the other case less or equal. So if it's the case that it cannot be equal in both cases, right? Because in that case, there will be an intersection between the two sets that are supposed to.
Yeah, for sure. So so remember here that the separating hyperplane theorem, right? Essentially, can tell you that there is a tangency point, right? But here, one of the sets is not closed, right? So one of the sets here is an open set, which is the upper contour set, right? So it's kind of missing the peel, the peeling part, right? So that's what's going on. But so you know, you have two convex bodies, and then, you know, both are convex. The intersection is empty, right? So hence there exists a hyperplane that can separate them. Okay. And now imagine, for instance, you have something like this, right? Can I separate them through a hyperplane? No. Why? Essentially, one of the sufficient conditions is missing, right? This set is not convex, right? This is out of the set, so this is a non-convex. Okay. So non-convex. And then, of course, what you're seeing right now is that one of the sets is an open set, right? And the other set is closed, right? So the intersection is empty, but then there can be this line separating them, right? And that's what's happening here. Okay.
Perfect. Yeah, that was my question. Okay.
Okay. So you know, this is very easy in 2 dimensions. You know, is a result in convex analysis because it is done for more dimensions, right? Now, but for 2 dimensions, it's trivial. Of course, we're doing something more complex. Okay, so the separating hyperplane theorem tells you that there exists a hyperplane, which is characterized by this vector and this r, right? Remember that this constant and the vector, right, characterize fully a hyperplane, high dimension. So this is normal vector and the direction. And this is just telling you that any element in the capital set V, you know, has to be above this R multiplied by prices. And in the set of feasibility, so the capital Y plus omega, the opposite inequality happens. Okay. Now, now it comes the harder part, right? So we want to remember that we want to show this is a price quasi equilibrium with transfer. So that has 3 conditions. First, firms have to be profit maximizing. Okay. Second, consumers have to be doing this condition that is very similar to consumer minimizing expenditure, right? It's not exactly utility maximization. So this is condition 2 in the definition of price quasi equilibrium. And then condition 3 is market clearing. So the rest of the steps are going to be designed to show that this price system is gonna induce a price quasi equilibrium with transfers, okay? So the first thing that we want to show is that every individual has this property that we define, right? And this is the role here. So if I have that xi is preferred to xi star for every I, then, you know, I'll have the multiplication of prices times the summation of all allocations of x is above R. So suppose that xi is preferred for every I, then by Lockean association, for each I there exists an x hat close enough to xi such that x hat is preferred to xi. And thus, by definition of the VI sets, x hat belongs to that set, okay? Now, if I take the summation of the xi hats, they also belong to the capital V set. And then if I multiply them by prices, then since they belong to the V set by the previous steps, we know it has to be above R. Now, if I take limits of the x hat, so tending to x, then the limits will be, essentially, if you take limits of a weak inequality, the weak inequality will be preserved. So that is not true of a strict inequality, right? Taking limits in an inequality that has weak inequalities will be preserved if you take limits, right? So now this essentially shows this inequality I wanted to have. Now, so this is a preliminary step. This is the thing I wanted to show. And I did it using Lockean association and the previous results, okay? Now, step 6 wants to show that if I multiply the xi star allocation times prices, this is equal to the multiplication of prices times omega, the economist endowment, plus the summation of all production plans for all j. And all of this also is equal to R. So this is just telling me that this allocation, x star, y star, that is a Pareto allocation, lives exactly, right, at this level R. So it's exactly the line that passes through the Pareto allocation, right? So given a step 5, we know that P multiplied by xi star is greater than or equal than R, okay? Also, xi star is equal to the summation of yj star plus omega. So this is just by definition of Pareto optimality. If you are Pareto optimal, you have to be feasible. So this happens here with equality. And now I know also that this belongs to the feasible set, so y plus omega. That means that because it belongs to the second set, y plus omega, by the previous steps, this has to be such that p times the summation of xi has to be less than or equal than R. So putting the two inequalities together, it has to be that this is equal to R, okay? Now, since the summation of the xi star is equal to the omega plus the summation of the yj's, we also have that p multiplied by the summation of omega plus the summation of yj is equal to R. Okay, so this is just telling me that the Pareto allocations live just where the hyperplane separates the two sets, right? One of them is open, so a little bit of step 5 is to take the closure if you want. That's why we take limits, right? And the other is closed, right? So now we're just finding exactly where R passes. Okay, now we have done it. So that, in other words, has pinned down the R. Now, step 7, we want to show that for every firm J, we have that the multiplication of P times Yj is less than or equal to P times Yj star. So who recognizes this inequality? This is telling you that Yj star has to be profit maximizing, right? We want to show that. So for any firm J, and Yj in a production set, capital Yj, we have that we can separate the sum into a term that has only Yj, and then a summation that excludes Yj from that, okay? And therefore, if I take this multiplication, because this belongs to the feasible set, it has to be that P times omega plus Yj plus the excluded summation where I remove J is less than or equal than R. Now, I know by the step 6 that this is not only equal to less than or equal to R, is actually equal to R. So we have R is equal to P times omega plus Yj plus the summation excluded H. Now, if that's the case, now what I'm going to do is the following. So look at this summation, right? This is equal to R, and the other summation where you remove the Y star and replace it by Yj, right? That is, any other alternative that is feasible has to be less than or equal than R. So if I combine these two things, it means that just combine this inequality with a second. All the summation that excludes J is canceled out, right? Omega is canceled out. So the only thing that remains is P times Yj. And this is less than or equal than P times Yj star, okay? So together, this implies that this thing here is giving me the inequality of profit maximization, okay? So in other words, right, what we're showing in step 7 is that the Yj star has to be in the boundary, right, of the production set. So it's an efficient allocation that is profit maximizing, okay? Everyone understands what happened? So the key of this step is this part. So you have omega, and then you change the summation from Yj star and you introduce just Yj. But this omega plus Yj without a star plus the summation of Yj stars remove J is still a feasible element, right? In the aggregate. This element belongs to the capital Y set. Do you understand that? Because it's a production plan that is feasible and you're adding production plans that are feasible plus the omega, it belongs to the set omega Y plus omega. So by definition in the previous steps, we know that elements of the Y plus omega has to be multiplied by prices have to be less than or equal to R, okay? And then by the previous step where we show that the optimal allocation Y star, so the Pareto optimal, and multiplied by prices plus omega, it has to be exactly equal to R. Now I just combining these two inequalities, and then P times omega cancels out. a summation of y h star according to all j different from that, you can also cancel out. And the only thing that remains is p times yj less than equal p times yj star. Okay? So together, this gives me profit maximization. Understood? Okay, good.
There is something I don't understand about the notation in profit maximization. It's like I read as it is revenue instead of profit, because
no, it's not revenue because Y is the production plan that has positive entries and negative entries. Negative entries are costs.
Okay,
so,
okay, understood. Okay, get it.
But it's true. So all of these things like revenue or cost, they can be written as a multiplication of prices times something. Profit just allows the Y to be negative and positive. So this is the net object, okay? Now, finally, step 8, we want to show that for every individual, if I have a allocation xi that is strictly preferred to xi star, then remember the condition 2 in this world. So we wanted to show exactly that p times xi is greater than or equal to p times xi star. So this replaces utility maximization in the equilibrium with transfers. This is what makes quasi-equilibrium different from equilibrium, right? So the only condition I want to check is that if I have an allocation that is strictly better than xi star, then it has to be that the allocation that is strictly preferred is weakly non-affordable, okay? In order to show that, consider any xi that is strictly better than xi star. Because of step 5 and 6, we have the following. First of all, if I take this summation of allocations and I remove the xi star from individual I, and then this is still a set in the upper contour set, right? So this means that this must belong to the capital set B, capital D set. Now, by definition of the separating hyperplane, it has to be that this element is greater than equal than R when multiplied by prices. Now, as opposed to this, if I collect all the xi stars, because this is in the Pareto allocation, right? P times xi star plus the summation of the x star h, then this thing has to be equal to R exactly. So the first thing is above the second, and now I just cancel out the terms with the summation of respect to subindex h. This dies off, and this gives me that p times xi is greater than or equal to p times xi star. So in other words, right now I have shown that this is a price quasi-equilibrium with transfers. I found a price system. I show that this price system induces firms to profit maximize. I've shown that this induces consumers to do this condition, that X, so expenditure minimization, call it. And then I also show that markets clear, okay? All of this is possible because capital Y, the production sets are convex, and the preferences are upper contour set is convex. It's also possible because of local non-association, okay? Now, there are some caveats here. First of all, remember what is the use of second welfare theorem. The second welfare theorem essentially tries to implement a Pareto allocation, right? So there is a central planner. The central planner picks one of the Pareto allocations in the economy and is trying to find a price, right? Like Uber, right? The price search. So it's trying to find a set of numbers, right? A vector of numbers that when given to consumers and firms, they will take it as given, right? Price takers. And then they will use it to make decisions, right? Firms will profit maximize and consumers won't utility maximize here yet. That's the difference with quasi-equilibrium, right? They won't maximize utility yet. They only have this expenditure minimization behavior. So if something is strictly better than xi star, then it has to be weakly non-affordable, okay? And then you also have that market should clear, okay? So right now we have constructed this thing that is almost the same as an equilibrium, but not quite yet, okay? Any questions here? No, okay. So step 9, right, is we want to show that the wealth levels, remember that we can collect all money from the economy and then redistribute it in gold coins. So the well levels WI are just constructed by multiplying the price that I generated times the consumption bundle XI star. And now I support the X star Y star P as a price quasi-equilibrium with transfers, okay? Now suppose that for every individual I, so what we're gonna do now is we're gonna mine the gap between the quasi-equilibrium and the equilibrium, right? So suppose now that the consumption space is convex, the zero belongs to the consumption space, so you can consume nothing. And also the preferences are continuous. Then any price quasi-equilibrium with transfer that has positive income profile, so the gold coins that you receive are strictly positive, is a price equilibrium with transfers. So in order to prove that, so in other words, right now we prove just that you can implement Pareto allocation by means of a price quasi-equilibrium with transfers. Now, here in lemma 10, we say that the difference between quasi-equilibrium and equilibrium is merely technical. So we have some convexity on the consumption space, we allow inactivity, 0, and then we also add continuity of the preferences. And then it turns out that any price quasi-equilibrium with transfers that has positive income profile is also an equilibrium with transfers, okay? So in other words, the proof we did, it's okay, right? So even if we prove it for the quasi-equilibrium, the difference with equilibrium is not much. It's up to technical conditions, right? Purely technical. So in order to prove that, so we're gonna show this lemma that is super simple. So in fact, I'm gonna skip the proof, but I'm gonna read lemma 11. So assume that xi is convex and the preferences are continuous. Suppose also that the consumption vector xi belongs to this xi. The price vector p and the well level wi are such that xi is strictly referred to xi star, and then this implies that p times xi is greater than or equal to wi. Then if that assumption holds, then if there is a consumption vector xi prime such that you are weakly, strongly affordable, so there exists a cheaper consumption, it follows that xi is strictly better than xi star, implies that p times xi is strictly greater than wi. So this is usually called the existence of a cheaper bundle. So if such a bundle exists, then you can strengthen the inequality with this strict inequality, and then the gap between price quasi-equilibrium and equilibrium disappears. The proof is very simple. You can read it. I'm not gonna spend more time here. So we just want to summarize the following. There are two main results in general equilibrium. The first welfare theorem says that you can, any allocation that comes from a price equilibrium with transfers is Pareto optimal. And this holds only under local non-association. So it's super weak, okay? So essentially this, I discussed with you this at length. So this is about the power of decentralization, right? So essentially, if you want to generate a Pareto optimal allocation, you can just let firms profit maximize, consumers utility maximize, and the market's clear. And then if price is formed, right, this price essentially will generate a Pareto allocation. So this is the first welfare theorem. The only thing you require is, of course, local non-association. Now, for the second welfare theorem, this is a theorem about a market design. So you want to take a Pareto allocation and you want to implement it by means of a decentralized system. So you take a Pareto allocation, and then there is a set of sufficient conditions that allow me to implement it through a market system. The set of sufficient conditions are preferences are convex, production sets are convex, right? And then preferences are locally non-associated. Now, if you want to go the whole way, you also need to have that preferences are continuous, right? That the consumption set is convex, and taken all together, right? You have that you can take any Pareto allocation and then find a price that will generate the whole thing. Now, so one again, so this is the second welfare theorem that is about implementing by means of prices an allocation. Okay. Great. So any questions here? So this kind of ends these two main results of general equilibrium. The first one is, again, the first welfare theorem, very, very powerful. The second welfare theorem falls under more assumptions, so it's less powerful, but in a way it's very interesting, right? Okay. So any questions here? No? Okay. So here, so in other classes, usually when we have studied the sparse max consumer.
Sorry, Professor. Sorry,
yeah.
just so basically those theorems, like it's all very theoretical, correct?
Sure.
Because it's all under rational, again, assumption of rationality, correct?
Yeah, for sure. So remember then that the role here of econ, right, was that we started from a utility maximizer, right, rational agent, and then all of these things happened when rational agents behave, right, in this very specific way. So this is just taking to the market the assumptions that we made in the chapter 3. Now, what Irina is saying is essentially, can you use this to defend free markets in real life? Not really, right? So we don't know, for instance, that consumers are really utility maximizing. Maybe they are not, or there is a fraction of people that are not, right? Also, people may fail to be price takers, right? People may have market power. So that also fails. People here are assumed to have full attention or full information. Maybe they don't, right? So maybe firms don't have decreasing returns, right? There may be some firms that have increasing returns, especially some new tech firms that are just starting and then actually are exploring a new area that has some section of their production functions increasing returns. All of those assumptions, if any of them fail, right, you're going to end up with this axiom, with these results not holding. So this is essentially the key of this. So yeah, for sure it's theoretical, but the way to understand this, and this is the way, the modern way to understand this. So you don't think of this as describing the real world. It is not a description of real world. This is a mathematical insight that is telling you that you can actually achieve, something socially desirable by means of designing your own market. Okay. So what I mean by that is the following. So assume, for instance, right, that you want to, for instance, allocate something like parking spots at Western, right? That's a typical problem of allocation, right? So this is telling you that a way to do this would be, for instance, to be able to implement it through a price system, right? So in other words, so for instance, imagine that there is an allocation of parking spots that you think is Pareto optimal, so no spot is wasted. So all of the spots are full. Now, this is telling you that you can just implement it by means of a price system. So you don't need to, assign to them, with something. You can just assign prices to them. So prices will be able to achieve the allocation you want in a decentralized way. So this is just telling you that, many things that people want to implement that are socially desirable could be implemented by means of prices, okay? Instead of, just command and control. Now, the fact that you're able to do it, that's more delicate. So there are a lot of people that dedicate their lives to market design, and that's, is a harder problem, right? And then some people have to take it to the real life, and then you actually have to do it. So again, one example of a little bit what the second welfare theorem is doing is, again, Uber. So Uber is not necessarily trying to get Pareto allocations, but for sure, they would like efficiency. So, but then within this set of allocations, they would like one that maximizes their profits, right? So in choosing that, they can essentially implement one price. And in order to do that, right, they need to know preferences and production technologies, right? So they are sort of doing the second welfare theorem. But again, they created their own marketplace, right? So this doesn't exist in real life, right? They created it, and then they collect information and so on. So the main message of the first and second welfare theorem is just that you can become an engineer and create your own market And in those markets, you can actually implement allocations by means of decentralized, systems and using prices as a signal. That's the only thing that this is telling you. This is not describing real economies, for sure. So that's one big mistake people did a long time ago, right? Was saying, oh, look, the first welfare theorem is showing that Adam Smith was right. The invisible hand is what's driving the world, and then the government doesn't have to do anything, right? That's not the case. This is just telling you that if you had a real market functioning very similar to our theory, then you could get actually really cool outcomes, right? So they don't exist usually in real life. So one idea is to implement them, right? So other people may think that you may try to make real markets look like these markets, right? But it's very hard, for instance, to force some individual to be rational, right? Maybe you can help them to be more informed, for instance, right? But you can also not force firms to be decreasing returns, right? If someone finds, some breakthrough in quantum computer, they're going to have some sections of, on decreasing returns, right? It's just the nature of it until they go back to some decreasing part. But, it's just, you cannot force things in real life. So the results here are just telling you an ideal setup in the vacuum that you could try to create more in artificially rather than you describe in real world. So yeah, that's the way modern people see these results. But yeah, they are not definitely describing real life for sure. Now, so since you haven't seen the sparse max, I'm going to skip this part. For the people interested, this 12.8 is just revisiting the general equilibrium and first welfare theorem, but with the presence of boundedly rational agents. In this setup, there is a boundedly rational agent that has limited attention to prices, and that fact essentially makes the first welfare theorem that does not hold anymore. Okay, you can read it if you want. Now, so with this in hand, we're going to move to the positive theory of equilibrium. And this is a very kind of dry chapter. It's very technical. So I'm warning you already. What is the objective? So once we have established the good things about the exchange systems in general equilibrium, we're going to now do some internal consistency checks. So remember the Walras mistake. So the fact that he believed that having the same number of equations than variables guarantee that the general equilibrium had a solution or had at least one equilibrium. So we know that's false. So any system of nonlinear equations, as the general equilibrium special case, can have no solution, can have one solution, can have many solutions. So until the 60s, people didn't know if general equilibrium had conditions that basically guaranteed that you had a solution. So a lot of the critiques of people that were called heterodox about general equilibrium, that wasn't the main dominant strain of a macro at the beginning, was that it was internally consistent. You don't even know if it exists. Point taken. This is in fact was an issue and wasn't solved since Leon Walras proposed this until the mathematicians that were bored about physics got into econ after the war. So a lot of great mathematicians came into econ. So Arrow, Debreu. Arrow was a meteorologist. Debreu was a French mathematician. So he was bored. He came into econ, and also an economist mathematician, Mackenzie. All of them were trying to solve this problem of existence of at least one equilibrium, right? So we're not going to prove uniqueness here. We're just going to show under what conditions we can establish existence of general equilibrium. So we're going to go back to the Walrasian equilibrium. So we have seen this before. So we have an ownership system theta. We have preferences and production. And then we have an allocation x star, y star, and a price vector constitutes a Walrasian equilibrium. If profit maximize, firms utility preference maximize with endogenous budget, and then markets clear. So just a reminder. Now, we're going to define with this what is called a pure exchange economy and an excess demand. So A pure exchange happens when the production plan is just the predisposal technology, right? So this is equal to, there is only one firm, and this firm is equal to minus RL plus. So I explained this to you as imagining there is a garbage can, the Edgeworth box, can happen in a laboratory. There is two people, two subjects exchanging things. The experimenter gives them endowments, so 10 apples, 10 oranges, splits them in some way between subject A and subject B. And then in that room for the experimental setup, there is a garbage can. And then each consumer can freely dispose of the apples and oranges there, right? So the only firm in that world is a garbage can, okay? Do you understand? Okay, we're going to study that special case because even in that special case, the proof is very involved, right? So we're going to just try to make it as simple as possible in a way. So in this setup, we're going to rewrite the three conditions above of our rational equilibrium in a simpler way. So first of all, we're going to assume that the total endowments of the economy are going to be strictly positive. Now we can redefine the rational equilibrium with pure exchange as follows. So first of all, the only firm that exists profit maximizes. That means, in fact, that you multiply prices times the y, start is equal to 0. And then prices has to be weakly positive. And then y1 start has to be less than or equal to 0. So that means people can only throw things away. They cannot produce anything, right? And then, of course, in this setup, profit maximization happens at 0. Now, you have that consumers preference maximize. And here, Mascolel does a bad notation thing, but I'm just connecting with the book. So Mascolel uses in this textbook, and I'm using it as well, the notation x sub I, and just calls it the well-rationed demand function. So remember that this demand is supposed to come from utility maximization, right? So in fact, I'm gonna write it here because, so xi of p c dot omega I is exactly coming from the R max, right? Maximizing x of the subject of the utility subject to the budget constraint, right? Okay, so this thing here has to be result of maximizing the utility function, okay? So this is the notation here, this is the xi. So this is capturing a lot of information, is essentially telling you that the consumer's preference maximized, okay? But it is in a way that there is already a demand function going on here. And now, finally, market's clear. So remember that there is only one firm, and essentially you have that the summation of the consumption xi is equal to whatever people dispose plus the endowments, okay? So a simple example. So say there is a demand function. This is the allocation x star, right? So it's just a vector. So x sub 1 of individual 1 is consumption of 2 units of good 1, 2 units of good 2. X2 is the same. And then endowments are omega of apples are 5, oranges are 5. Then the endowment of individual 1 is 3, 2. And the endowment of individual 2 is 2, 3. Then you have the disposal technology. So you have here that apples are going to be 4 minus 5, so minus 1. And then oranges are going to be, for instance, 4 minus 5 is equal to minus 1. So here you're going to just dispose of 1 apple and 1 orange. And then prices are going to be 0, 0. Then you can check all these conditions. And then essentially, you can show by looking at these conditions that this constitutes a well-rational equilibrium, okay? So this is just a situation where these individuals are such that they only like to consume 2 units of each item. So whatever unit is above that target, right, they will dispose it away, Okay, they will throw it away. So this is just showing that there are conditions, right, under which you can have people disposing of alternatives. Of course, here the assumption that is missing is local non-satiation. So these guys essentially like only 2 apples, right? That's the optimal bliss point. And if they go beyond the bliss point, they decrease their utility, right? So they are locally satiated at 2. So here, because there is kind of extra units of apple and oranges beyond the bliss point, they will dispose of it, okay? And then in this system, right, prices are equal to 0 because there is abundance of both goods, right? So there is extra goods, so they don't really need to, they don't need to exchange. There is no opportunity cost. They just consume their endowment, right, and dispose of one of them, okay? So this is a very special, you know, a special case of well-rational equilibrium. You know, this is something that you may see in exams, right, in core exams, not by me, but this is something you have to be prepared for, okay? So again, this shows the importance in this second part of the class of definition. So the definition here allows for people throwing away some of the things that you have as an endowment. And this may happen, of course, in some situations. One such situation is in a violation of the local association, okay? Yeah. Now, so I'm gonna make the first proposition and proof of this chapter. So in a pure exchange economy in which consumers' preferences are continuous, strictly convex, and locally non-associated, prices are weakly positive, and they are a well-rational equilibrium price vector, even only if the summation of all individual demands for all individuals I to capital I is less than equal than the summation of endowment. So in other words, in this setup, we are going to show that if this condition holds in the aggregate, which is called the excess demand. So if excess demand is less than equal than 0, then this constitutes this price at which this happens. This constitutes our rational equilibrium. Okay. So this equation here essentially captures the whole well-rational equilibrium for this special case of pure exchange. If prices are weakly positive, is a well-rational equilibrium price, then 1, 2, 3, the conditions above imply this inequality. So that's easy. So essentially, this follows from replacing in the market clearing condition. It follows for basically replacing the XI, which is the well-rational demand. And this follows also from the inequality of profit maximization. So if you put this together, you get this inequality. Now, if the other side is the difficult one, so if you have this excess demand is less than equal than 0, then you define the Y1 star, which is the optimal production plan on the only firm, the garbage can. This is equal to anything that was not consumed. So this is the summation of the XI demands minus whatever exists in the economy. And then we have to check that the multiplication of prices times this quantity that I define is equal to 0, because profit maximization here happens at 0. So prices times the Y1 star production plan is equal to 0. So this follows from local association, and then we just let that XI star is equal to the demand evaluated at this price. So 1, 2, 3 hold, okay? So again, this is about naming. So we know that the difference, which is a vector of the demand of goods of each individual I minus the omega I, is the consumer I net or excess demand for each good according to what he had in terms of endowments of the given good, okay? So now, this is a definition. So excess demand function. So the excess demand function denoted by Z of P is the difference between XI evaluated at prices P at a given endowment, and now the endowment becomes fixed for now on. So it disappears from the arguments. This is called excess demand. And yet again, this is excess demand because it's whatever the consumer wants minus whatever it exists in the economy, okay? Now the aggregate demand function in the economy is just the summation of the individual excess demands, okay? And this is a mapping when the endowments are fixed is a mapping from the RL prices that are positive to RL. So this is just telling me for these given prices, how much excess goods there are in the economy. Of course, you may also be, this can be negative or positive, right? When it's negative, then essentially you're in an equilibrium. When it's positive, you're not in equilibrium, okay? And then finally, we have this corollary from the previous observations with a change of notation. So we say P, a vector in RL plus, is an equilibrium price vector even only if the set of P is less than or equal than 0. So this notation here is very minimalistic, but it's capturing a lot of information. So ZP is essentially telling you that there is a system of nonlinear equations that depend on L prices, right? And how many equations do I have here in ZP? I have L equations, right? One per good. Do you understand? So ZP is a vector that has dimension L, right? So there are L goods here. So it's a vector value function, okay? So this thing here is giving you L goods excess demand. So this is in general is nonlinear, it's highly complex. So it's describing a nonlinear system of equations, okay? And you're saying that if this thing is less than or equal than 0, then whatever price makes this set of P less than or equal than 0 entry-wise, because it's a vector of size L, then P is an equilibrium, okay? Now, if you have some good at which excess demand is exactly equal to 0, and the prices of that good is strictly positive, thus at equilibrium, a good L can be in excess supply, right? Strictly less than 0, only if it is free, okay? We can add additional assumption in terms of reference to strengthen the previous definition. For instance, we're going to require that all preferences are strongly monotone. So if consumers' preferences are strongly monotone, continuous and strictly convex as before, strictly positive price vector is a well-rational equilibrium price vector, even only if it clears market. That is that the ZL is exactly equal to 0 for all L, okay? Do you understand? Good. So now, what people do in real life, especially if you go to macro, so it will be very rare if you have less than or equal than 0, right? Less than or equal to 0. Usually, when people work in real life, consulting, macro, then they will use this definition with set L of P is equal to 0 for all L. So essentially, this is a system of equations where you have exact market clearing. There is no excess supply. So usually, you know, in real life, it's very hard to study markets where there are free goods. So people usually don't study them much, right? There will be a very special weird case. So, you know, for all practical purposes, this thing is what matters, right? But this happens under a strong monotonicity. Okay? So the more the better, strictly, then you know you don't have to look at the excess supply of things. So again, one example of a violation of strong monotonicity is this example here, right? Here you have satiation at 2, right? So this is not strongly monotone. And then you can see that there is excess supply of one orange and one apple, right? And hence this only happens at price 0, right? The price vector that markets clear this thing is 0, 0. Okay, do you understand? So this is an example of things that can happen if you don't have a strong monotonicity. Okay, guys. So here, before moving to the last part, yeah. So I want to take so let's do a 5 minutes break. So we restart at 2, because now we're gonna just go to the crazy part, which is the existence proof, right? So we need some stock. Okay. So see you in 5 minutes. I'm just gonna stop recording. Hi guys, can you hear me? Okay. So let's go to the difficult part of the class. So right now we're gonna introduce a result that is super simple, but then we're gonna use it in order to prove existence, right? So suppose that for all individuals I, preferences are continuous, strictly convex, and convex and strongly monotone. Then suppose also that the endowments are strictly positive. Then the aggregate excess demand function set P defined for all price vectors P satisfies the properties. So this is just an implications of the assumptions, right? The excess demand is continuous, easy. You have demand functions that are continuous, and the continuity and the rest of assumptions. So then the summation of excess demands are continuous. Z is homogeneous of degree 0, consequence of utility maximization, right? Then prices multiplies by Z of P is equal to 0, consequence of Walras law, coming from strong monotonicity, which implies local association, right? So we prove that under local association, then you have to live at the budget line. So prices times Z P is equal to 0 is the general equilibrium version of the Walras law, okay? And then the only two things to understand a little bit is bounded below. There is an S, constant S, such that set of L of P is greater than that constant. So this is bounded below for every commodity L on any price. So this is just telling you that you cannot have, because prices are positive and things are desirable, right? You can never have excess demand too much, right? Because essentially this is creating a bound S. So the assumptions here create this bound, and we're not specifying exactly the bound, we just know it's finite. And then the final one is that if you have a sequence of prices such that there is some price that goes to 0, then if you take the maximum of this set of excess demands for all goods across the goods is taking the maximum with respect to L, then one of them will go to infinity. So that means that because things are desirable, a strong monotonicity, if something becomes free, then people will want it, you know, infinite amounts of it, because everyone, you know, is strongly monotone, you want it. Now it becomes free, demand becomes infinite, right? So that's what's happening here. Of course, you're not going to have an equilibrium there, but this is possible in the function. Any questions here? But these are implications of the assumptions, nothing fancy here. They are important because we're going to use these properties in order to show, you know, the next result. Now, one thing here that you have to realize, yet again, due to homogeneity of degree 0 and Walras law, remember that we know this lesson from before. There is always one redundant market. Do you remember that? So if you have, you know, L goods, you have market clearing conditions for L goods. Then if you clear L-1 markets, then the final Lth market is going to be automatically cleared. So that means I can take this system of nonlinear equations and reduce the last market, eliminate it, scratch it, and then you're going to get a reduced system called C hat, right, from L to L-1. And if the system is in equilibrium, so capital hat ZP is equal to 0, then the original system is again in equilibrium. So this is just, you know, rehash of things. Okay, so can you hear me well? Okay, so it seems that now I'm moving to the microphone here because my headphones died. Okay, so great. Existence of Walrasian equilibrium. So here comes the nice thing. So suppose that ZP is a function defined for all the strictly positive prices. So this function essentially, you know, for all prices in the domain, the function has a value. And satisfying the conditions 1 to 5 that I just described. So these conditions, okay? Now, then the system of equations set P is equal to 0 has a solution. So what it means to have a solution? It means that there is a price such that Z evaluated at such price is equal to 0. Okay? It doesn't mean that there exists only one price. It means that there exists at least one price. Okay? Now, we don't care anymore about less than or equal to 0 because we are assuming a strong monotonicity, right? So only quality matters at this stage. Now, hence, our Walrasian equilibrium exists in any pure exchange economy in which endowments are strictly positive and every consumer has continuous, strictly convex, and strongly monotone preferences. So, this proof, you know, seems like
not a big deal, but it took a while, right? So people couldn't really figure out how to prove it. So we're showing essentially that any system, in any dimension but finite, when essentially satisfies condition 1 to 5 that follow from assuming that consumers have continuous, strictly convex, and strongly monotone preferences, right? This will imply together, right, that there is at least one price at which markets clear for all markets. Okay? So why this took so much to prove? Well, so who has seen A Beautiful Mind, the movie about John Nash? That. So a lot of you have seen. Yeah. So John Nash is famous because for many things. He has results in math, in differential equations, in bargaining theory. But he's mostly famous because he essentially showed the existence, of an equilibrium in games, in strategic situations, right? And he showed that there is possibly a mixed equilibrium in a situation where there are different decision makers interacting in a strategic situation. This is called the Nash equilibrium. So he wrote this as a note in the proceedings, this famous journal. And you see the paper published is very small, right? So when he was working on this as part of his dissertation, he had some issues and he was trying to prove some things. So the proof was very long. And then the story says that he met John von Neumann, right? Von Neumann is one of the geniuses of the 20th century, right? Mathematician, economist, physicist, computer scientist. And, less appreciated than Einstein because he didn't have nice hair, But, he, of course, was super genius. And a lot of us are super influenced by him, right? And so he approached Nash and saying, "Oh, that's only a fixed point theorem." So in math, a lot of people were working on fixed point theorem. Fixed point theorem, so we're going to describe them a little bit more later. Essentially, is the following idea. So imagine you have a map, a function that is mapping from R to R. So it maps from the domain, and essentially the image is the same. And then, this mapping, this kind of mapping will have a fixed point whenever you find a particular point in the domain, let's call it X star, such that if I evaluate F at X star is equal to X star, right? That's why it's fixed point, right? It's the same in the domain as in the image, okay? So this is a nice mathematical object to study, and a lot of mathematicians at the time Nash was working were working on this problem. So, the original fixed point, was Brouwer's fixed point, which was very simple, just using functions. But then, you have to generalize it to correspondences that we study in chapter 3, right? The consumer theory. We study what is a demand correspondence. So with correspondences, things get hairier. And then, Kakutani worked on this problem, and there is the Kakutani fixed point theorem. All of these, Kakutani's fixed point theorem and Brouwer's, are in the Mascolel mathematical appendix, and you can read it even in Wikipedia by this time. So, they are so popular now, but at the time of Nash, this was, very new. People were just working on it, and only the well-connected people knew about it. And in fact, von Neumann knew about it, so he told Nash, "Look, this is just an application of the Kakutani's theorem." So Nash saw it, and then he simplified his proof. And then, he sent to the PNAS. And the proceedings, is super small because of that. So he had to update the proof as opposed to the dissertation. So Nash, proved using fixed point theorem that there was an equilibrium in games. Now, you remember that games are much newer than general equilibrium. General equilibrium is going on since Walras, right? But there was no proof of existence. So then, Mackenzie, Arrow DeBrew saw the piece in the proceedings of Nash and said, "Wow, this tool is so cool. Fixed point theorems are all the rage. They are the new thing. Let's get into the train. Let's try to prove it." And they started essentially trying to see how to cast general equilibrium setup into a fixed point theorem friendly setup. Okay, so that's what they did. There was two competing teams, Mackenzie and then Arrow and DeBrew. Arrow and DeBrew, they got together, right? And they competed against Mackenzie. And they essentially provided the result here. Now, most people know this result by only Arrow de Breu, and that's because Aaron de Breu kind of played dirty with Mackenzie. So de Breu was an editor of Econometrica, and he essentially was sitting on the Mackenzie paper until they were able to fix the proof with Arrow. So, you know, that's part of the soap opera. There is a book about that, so you can get it in Amazon. So the people that say econ is boring, well, it is a bit, but sometimes it has fun stories like this. And so you got the Arrow de Breu versus Mackenzie. So Mackenzie was a big deal in Rochester, and de Breu, you know, and Arrow were, you know, in bigger universities. So you can imagine that that has also something to do with it. So econ is very elitist as well. But in any case, so remember the whole story. That's for you to remember, hopefully with the stories as a memory aid, that the whole deal with this right chapter is that we want to recast general equilibrium in a way that is friendly for applying the famous fixed point theorems. If we're able to do that, then we are just going to invoke Kakutani, right? And then we're done, okay? So the rest of this part is going to just rewrite what we did with excess demands in a way that is friendly for applying a fixed point theorem. That's all we're going to do, okay? And then once we have done it, then finally you are sure that you can apply this to your model. So how do you use it in real life? So applied people don't get discouraged. So essentially a lot of you are going to work with models, right? Even if you become a consultant, right? So I actually work with these kind of systems when I was a consultant. So I was hired when I was just in the middle, after graduating from my master's and going to a PhD. I was working for the European Union. So they, you know, they were interested in doing some predictions of the Ecuadorian, where I'm from Ecuador, Ecuadorian economy, you know, using a general equilibrium, you know, setup. So, you know, with one of my colleagues, you know, we built, you know, a general equilibrium model, and essentially you have equations for several markets, you know, the labor market, you know, the manufacturers market, agriculture market, and then you also have, you know, equations for consumers. You know, you can, in our case, we have demands for different quantiles. So you have, you know, the very, very poor people, the very rich people with different demands and so on. You have also equations for the government, you know, whatever. So you form, you know, this system of equations, very nonlinear. You do your work, you estimate parameters using econometrics, good data, and so on. You do all that. And then you have to be serious, right? As a modeler. So what is the first thing you have to do when you have a system of equations? You have to be sure it's internal consistent. So you have to show that this thing actually has a solution, right? If your system of equations doesn't have a solution, then it's internal inconsistent, is worthless, okay? It's not good, okay? So then, you know, you actually have to do this. So do you have to do it from scratch and show, you know, that your very complex system of equation has a solution? Well, I know micro, so you can go to these books and then check whether your model satisfies these conditions. Of course, there is a more complex version of this theorem allowing for production, right? Essentially, you require the production set to be convex. So it's nothing extra. It's just the convexity of the production set. And then together with the utilities being continuous, strictly convex, and strongly monotone, then you're fine. So for instance, in our setup, we were using CES utilities. CES utilities happen to be strictly convex, strongly monotone, and continuous. So then you know already that these things are satisfied, right? And then you already know, thanks to these guys, that your model has a solution, okay? So in fact, you know, these are things you have to know because then you can apply them. Now, the issue is if you want to break these assumptions, so for instance, we want to have some very weird non-convex preferences, then you have to go from scratch and try to prove it yourself, okay? So this is yet another reason you may want to use these assumptions, okay? Now, with all that thing, trying to get out of the dryness of the result, let's do just the casting in the fixed point setup. So first of all, we're going to normalize prices. That means I'm going to just remember prices can be changed because of homogeneity of degree 0. So I'm just going to normalize it in the following way. I'm going to make it such that the summation of the prices is equal to 1. Now, if the summation of prices is equal to 1, and prices are always non-negative, Then this gives you a simplex. So the simplex already appear in the lotteries section. Remember that the lottery was described by a simplex. So the simplex is any vector, right? Is this collection of vectors such that they add up to 1 and they are non-negative. Okay. So prices here, mathematically, they look the same as probabilities. They are not probabilities, of course. They don't have anything to do with probabilities. But mathematically, they just became the same thing, right? Is the simplex, this triangle. Now, we're going to do this because of a reason. When applying the Kakutanis theorem, the Kakutanis theorem is going to require that the domain of the fixed point has to be compact. A simplex is compact. A compact set is going to be a convex set as well. So it's going to have a lot of nice properties. So instead of dealing with an unbounded set of the prices, which is, R plus the positive Orton, then I'm just going to make it compact. So this is a way of compactifying this thing. Okay. Now, because of the function, the excess demand set is homogeneous of degree 0, we can restrict ourselves in our search from an equilibrium to price vectors in the simplex. Now, take the simplex and then separate it into two objects. First of all, the interior of the simplex, which are things that are strictly positive, and then the boundary, which are things that can have 0 entries, right? And then what is going to be the proofs plan? So first we construct a mapping from the simplex to the power set of the simplex. So remember that I told you what is a fixed point, right? Now, a fixed point with function is super easy. So take the mapping F and evaluate it at X star. It gives you out X star. X star is a fixed point. With the demand correspondences is analogous. So we have a fixed point. If you have P star belongs to the image of F of P star. Okay? This is a fixed point for correspondences. Do you see the difference? So in other words, there is a point in the domain, P star, that is also in the image. Now, the image of this mapping can be a set because it is a correspondence. Okay? That's the only thing that has changed. And now we're going to show that after creating this F, using the general equilibrium setup, we're going to create an F based on the excess demand. Once we have created this F, then we're going to guarantee that if such a fixed point exists, then this same point, P star, is going to be an equilibrium. And then third, we show that F is going to have some properties, right? And then finally, we apply the Kakutani, so it's going to be convex value and upper continuous. And then we apply Kakutani's fixed point theorem to show that at P star, with P being a fixed point, this is going to necessarily exist. So in other words, I'm going to create an F from the general equilibrium setup, and I'm going to use the properties of general equilibrium, 1 to 5 above, of the excess demand, to show that F has the properties I need to apply the Kakutani's fixed point theorem. So using 1 to 5 above of the excess demand, I'm going to show that there is a general equilibrium under these assumptions. Okay? So this is exactly the plan of the proof. Any questions here? This part is very important that we understand what's going to happen because the rest is super, super long and complex. And so it's not going to be about conceptual complexity, but it's going to be about tediousness of constructing the F. So the F is constructed in a very convoluted way that took years for Arrow and DeBrew, right? So, but the thing I want you to understand first is what we're trying to do. So essentially, we want to construct a fixed point mapping, a self-map that's going to have a fixed point property. And this fixed point property is going to hold only under the assumptions of the excess demand. Okay? And once I have cast this into a fixed point problem, then I'm just going to apply Kakutani's fixed point theorem in the Mas-Colel mathematical appendix to conclude that there is a fixed point in the created mapping, and this implies that excess demand has an equilibrium. Okay? So that's going to be the plan. So let's do that. So step 1, I want to create the map F. So I'm going to let F of P be equal to all elements in the simplex Q, such that if I multiply a set of P times Q, has to be less than equal, greater than or equal to set of P times Q prime. So important thing about this notice that here I'm multiplying the excess demand at values P, right? By this other price Q, which is different from P. And then if this is greater than or equal to set of P times Q for all Q prime, then this Q belongs to the image of this correspondence. Now, of course, there is some kind of intuition why I would like to do that. Essentially, remember that you are in equilibrium whenever set of P is equal to 0, right? And by Walras law, I know that prices times Z is equal, the equilibrium price is equal to 0 by Walras law. So here by changing the price by another P, say some small deviation from the baseline prices P, then this is giving you an excess demand evaluated at a different price. So if at this given price, this is better, greater than or equal to any other Q prime in the simplex, then of course it's going to hold with equality when Q prime is equal to Q, but it can be strictly greater for other Qs. Then, this is kind of giving me the set of things that are out of equilibrium, right? But the real reason why people created these things, because again, it works. This is a part of the theoretical mind, right? So Arrow and Debreu were smart enough, had the spark to create this object, and they worked several years to create it, right? So don't worry and don't feel bad if you don't get exactly why you formulated FP as this, This is the product of years of work, right? And just right now we're giving you a line, right? So you're just seeing the end product, right? And this, this is, really work and inspiration, of two very bright guys plus years of strong, a lot of strong focus on work. So essentially what we're doing here is defining demand correspondence. No, it's not a demand correspondence, it's a correspondence. So it takes as an input prices, which is a vector in RL, and it gives you a set of prices, okay? So remember that the definition was a mapping from the simplex of prices to the power set of prices. So the image of this is not only one price, but possibly a set of prices. Now, essentially, right, we have that FP is equal to Q, is equal to all vectors Q, such that if QL is equal to 0, if essentially set L of the excess demand of such a good is less than or equal than the maximum of L. So this is just an implication of the previous part. So remember here that if some price went to 0, right, then essentially, you have this infinite demand. Here you have that if the actual demand at P is less than the maximum with respect to all goods, then the price that is going to be satisfying the above condition has to be equal to 0. That's the only thing that works. So also notice that set of P is equal to 0. Then when this is the equilibrium, then the whole image of this object is going to be the simplex. So why is that? Because set of P is equal to 0 if I multiply it by any Q, right? And then essentially it's going to be above all others, right? Because it's always 0. So it's going to be 0 is equal to 0. So that means that by construction, this object here is going to, whenever you have an equilibrium, then the image of the correspondence is going to be the whole simplex, okay? So this is the important part about the F. So F is going to be such that if there is an equilibrium price, then the image is going to be the whole simplex. So this will guarantee that there is a fixed point, right? Because the whole simplex contains the equilibrium price, right? So that's the magic of this. Now, remember that we just have defined F of P for interior prices. So P is strictly greater than 0. So remember that we separated the simplex into two objects, the interior, right, which has strictly positive prices, and the boundary, which is the part that is not in the interior, but is still in the simplex. So that means, right, that here we are just defining FP in step 1 for the interior allocations. And then step 2, is gonna define it for the boundary. So the boundary is gonna be cases where you have some prices equal to 0. So for the boundary, it is gonna be such that the Q belongs to the image of f of p. Whenever if you multiply prices with just the input times the Q, this gives you equal to 0. Okay, so in other words, this is gonna be QL is gonna be equal to 0, even only if PL is strictly positive. So with this construction, no price at the boundary can be a fixed point. So remember that essentially, when you have this definition at the boundary, you are ruling out that fixed points happen at the boundary. So there is no P that belongs to the boundary such that P is inside the image of f of P. So this will guarantee that, for instance, if the input price is positive, then the image in the boundary is going to be 0, right? So in other words, this is forcing the fixed point to not live in the boundary. So remember that the price that is going to mark it clear is going to be positive price, okay? So again, step 2 and step 1, they are done on purpose to guarantee that the fixed point happens at equilibrium and at an interior price, and that there is no other fixed point that happens at the boundary. Okay? You understand? So this is the whole reason why this exists. Now, so the step 3 is where we connect the excess demand. So a fixed point of FP is a Walrasian equilibrium. So essentially, we're going to show that if you are in equilibrium, then you have to be a fixed point is a Walrasian equilibrium. So any fixed point of f of p that I created in the previous steps has to be a Walrasian equilibrium. Okay. So this is the part that is a little bit long, and in fact, I'm not going to go through all the cases. I'm just going to go through the main ones. So suppose that P star is a fixed point. So imagine in this case, this P star is in the interior, so it's a positive price. Now you have several cases. So if Z dot P star is different from 0, that means there are some entries which are not 0. Then according to the definition of F, it has to be that F of P star is strictly inside the boundary, right? So essentially, right? So if you are not in equilibrium, then this thing has to be inside the boundary, okay? So that means that if you are outside equilibrium, you are not going to be a fixed point, right? Now observe that if Z of P is different from 0 for all positive prices, because of Walras law, we have that Z of L is less than or equal to 0 from some L, and Z of LP is going to be strictly positive from some other different L prime. Then for such a P, any Q that belongs to the image of F of P has QL is equal to 0. So that is essentially by contradiction. So this P inside F of P cannot occur because the multiplication of P in inner product P is strictly positive because just a quadratic term. While P times Q is equal to 0 is the requirement to live inside this fixed point. So this must be the case that it has to be that P belongs to the image of F of P, and Z of P is equal to 0. So step 3 essentially says that if you are a fixed point, then you are an equilibrium. So the final part is about establishing that the F mapping has the properties required in the Kakutani's fixed point theorem. So any theorem holds under assumptions, right? So the first assumption is that the self-map goes from compact sets to compact sets. They are also convex. So the simplex is the domain set. So that's fine. Check. And the second is that the mapping is a convex value correspondence, so that the image of the correspondence is convex set. And the second thing is that is upper MA continuous. So upper MA continuous we also studied before, and is a weaker form of continuity for the correspondences. Again, if you need to refresh this is in the Mas-Colel mathematical appendix. We're going to just show that these two things hold, and once we do it, right, we're just going to be ready to apply Kakutanis. So at this stage, this part of the proof is merely technical. The previous part were the most important thing, the creation of the F. So the first thing is that case one, so if you have a price that belongs to the interior and a Q that belongs to the boundary, then F of P is a level set of linear functions defined on the convex set. Essentially, you have that Q belongs to the simplex such that there is a constant vector L. If you do the inner product with Q is equal to K, a scalar, and a vector L. And essentially, because of that, you have to be a convex set. So you just can combine these linear functions. And then the rest of cases are easy to verify. So, and then to establish upper MA continuity, you can consider a sequence of prices, P, and then a sequence of prices Q, such that Qn is in the image of F of Pn for all n. Then we have to show that Q in the limit belongs to F of P. So this is the definition of our upper MA continuity sequentially. And then, the rest of things is just verifying that this happens. The main thing to use here is property 5, such that if we have this set of L of Pn, this is below the max of L of set of Z sub L of Pn. And then again, because we're going to take limits here, this is going to happen. And then we have that QLn is equal to 0. So the right-hand side, remember that this is the max, goes to infinity per the property 5 of the excess demand. And then the left-hand side is bounded above, because if it is positive, then you have to have this inequality here with respect to the lower bound S. So we're going to use it. It's a little bit tedious, so this part I'm just going to skip, but you can read it if you are interested. So this is just the technical part, ensuring that you're going to have that F mapping is upper MA continuous and is going to be convex value. So convex valuedness, it was easy to show. The upper MA continuous requires a lot of cases, and then you can check them all. Now, so this is all about this step. And then finally, once you have the F that is convex value and upper MA continuous, mapping from a compact set to the power set of the compact set, then you just apply Kakutani's fixed point theorem that says that a convex value upper MA continuous correspondence from a non-empty convex set into itself has a fixed point. Since the simplex is not empty, convex, and compact, and since F is convex value and upper MA continuous, then we conclude that this mapping has a fixed point. Now, from the previous steps, we know that a fixed point is also an equilibrium. So we have established that essentially the general equilibrium setup has an equilibrium, that the system of equations set has an equilibrium. And then remember that this happens under conditions 1 and 5, which are implied by having consumers that have continuous, strictly convex, and strongly monotone preferences. Now, question for you guys, and with this we're done. So what happens, for instance, if I remove from this a strong monotonicity? Okay, so right now I no longer have a strong monotonicity. I replace it by local non-association. Will rational equilibrium still exist? Yes or no? What do you think, Amat? Are you listening to me? Cameron? Okay, so we have some inactive people. Random check. Okay, so the reason, this is a classical core question. Okay, so the fact that this assumption fail essentially means, right, that you may or may not have an equilibrium. So these are only sufficient conditions. Okay, so if you see these conditions together, then you know for sure there exists an equilibrium. If some of these assumption fails, then you are on your own. You have to prove it yourself by hand. Okay, so this is the key of all this, second part of the class. So it's differentiated between necessary and sufficient conditions. So right now I'm going to stop.